Okay, so number 3 tells us a region D is bound by the graphs of y equals x minus 3 squared minus 5 and y equals negative 1. Does anybody recognize that first equation and what it's telling us? Why is it in that form? Blast from the past. What's that? It's not point slope because it's not a line. What is it? Let's start there. If you expanded that all out, what would you end up with? A quadratic. So we've got a parabola. And what is this form telling us about our parabola? Nobody knows. This is vertex form. So we actually know that our vertex is, actually, let me write it out because we do have to change the sign. Vertex form is y equals x minus h squared plus k. Oh, I've seen that before, right? Yeah. So what's the vertex of our parabola? It is 3 positive, negative 5 negative. It is x minus h. So, I mean, this actually does, if you take that squared, if you take out the squared and put an m in front of it, you do actually have our point slope formula, which does do the same thing the way that we do it. You change the x value sign, but you leave the y alone. So they are similar for no good reason, but there are some similarities there to that one. But here we're finding a point on the parabola, and that point happens to be the vertex. So that's specific to this one. So when we go to make our sketch, we know that we have a vertex of positive 3, negative 5, which just gives us a clue of like where to put the parabola. If I had just given you the x squared minus whatever x plus whatever, you actually have to get this in that form, which would involve completing the square, to figure that out. So that's why they gave it to you there. Kind of helps you draw that sketch. Not anything that I'm going to ask you to do, but I think good to know. So there's my parabola through 3, negative 5-ish. And I have the line y equals negative 1. So we'll draw it like there. When I plug 1 in, I would get 4 minus 5. I'd get actually negative 1 as well. So my graph isn't perfect. But yeah, so there we go. All right. We probably do need these points for some point in here. So let's plug in. Let's set y equal to negative 1 and figure out what the x is. Negative 1 equals x minus 6x plus 9 minus 5. That would be nice, right? Yep. I was thinking I had to factor it, so I wasn't going to make a mistake based on that, but it was definitely wrong. So we have to factor, we actually have to do 9 minus 5 and then plus 1. So I think we end up with plus 5, which is an easy factor. So I did 3 additions, or I worked with 3 numbers there. I had a positive 9, I had a minus 5, and then I added 1 to bring it over to the other side. That's how I got the 5. And this guy is going to be x minus 5, x minus 1. Which means that these coordinates are 5, comma, and 1, comma. And because y has to be negative 1 there, those are the y coordinates. Even if you didn't know the vertex form on this one, get rid of your x and y axes and you still have the picture that you need. For the most part, you know where that line hits, you knew where to draw it. So you didn't need the vertex form to really do this problem, but it definitely helps. Okay, so we need the area of region D. That one should have been easy. You would do the integral from what to what? 1 to 5. Of what's going to be our upper function? Yep. -1 minus. If you are plugging a function into something that's being subtracted, please put it in parentheses, right? You've seen that a couple times now. So it's -1 minus the quantity, the other function, which is the lower function, which would be x minus 3, but squared, minus 5. Probably smarter. I actually didn't put it in parentheses because I stole my parentheses that I wrote. Probably smarter, since we already did it, to just put the expanded out form of that. So that would just be x squared minus 6x plus 9 minus 5. So that's going to be plus 4 dx, integral from 1 to 5. And now you should end up with actually the same thing you ended up here, just with possibly a sign flip. And that is what's going to happen. I'm going to have a -1 and a -4. So the -1 will combine with the -4 to give me -x squared plus 6x and then minus 5 dx. So sometimes it just depends on the problem. We always try to keep our x squared positive here. Sometimes that just isn't the way that it works out. But these two should match because we really did all the same math with them. Match or have a complete flip of signs because you're doing the same math either way. This one just had a negative in front of every single thing that you were doing as opposed to this one. Right. So I'll leave that one there. In which spot? No, so what I was only doing the right-hand side. So 9 minus 5 is 4. The 5 that I got in the next line came from also bringing the 1 into the picture. And the 1 is not brought into the picture yet here, if that makes sense. Yeah. Yep. I kind of made it seem like we were going to have this exactly, but then as I started doing it, I realized my combining steps there meant that if I was going to separate the steps here, it wouldn't look the same until here. Okay. So again, that's just an antiderivative. We're plugging 1 and 5 into it. Probably a bit of a pain. If you're pressed for time, throw it in a calculator. You get the answer. All right. Letter B says, let D be the base of a solid with cross sections perpendicular to the x-axis. The reason we say perpendicular to the x-axis and not parallel to the y-axis is that when you're working with cross sections, that letter we're giving you is going to be the letter that goes with the dx, right? It actually might make more sense to say parallel in general, but then you'd have to have a reverse association. So we always say perpendicular to an axis because that tells us the d, whatever, in this case, dx. We have a rectangle that is 3 times the width, and we've got to find the volume of this solid. Like everything else, when I change it from a square to a rectangle, it just changes the coefficient. So we are going perpendicular to the x-axis, so that means we are looking straight up and down. We're really kind of doing the same, we have the same two functions. So in this case, and this is how I did it in my on my review, I labeled the upper function f of x. In this case, the upper function is -1. I made the lower function g of x, and that's going to be the other guy, so x squared minus 6x plus 4. And then the area of this rectangle, because it's just got a height 3 times the width, is going to be the base times 3 times the base, because the width is just 3b, so we'll say 3b squared, which is 3 times f of x minus g of x, but squared. While everything's in front of us, this is a good thing to also notice. When we're working with cross sections, the two functions are subtracted and then they're squared. When we're working with volumes of solids of revolution, those formulas square the function or square the function and its adjustment first and then subtract. So they are very different formulas in that way. And then don't lose sight of this. There's a question on the review. There's a question on the test that's actually a little bit easier because of this. All you have to do, once you have that area formula, you integrate it. So this will be the integral, same limits because we're working with x's, from 1 to 5 of that area formula, 3 f of x minus g of x, but squared. And f of x minus g of x, again, is just this same thing from over here. So that would involve like a 3 by 3 multiplication. That's another one that's best for the calculator to get your final answer. It'll take you forever to get these things done if you don't. It says that. Use a calculator after you set up the integral. And I didn't write dx. Questions on that? And then last but not, or like at least kind of where I want to stop here, this is why I picked this problem. Let D be the base of the same solid. We've got the same thing, but now we're going to make our cross sections perpendicular to the y-axis. That means that the base of each of those cross sections, make it a little bit smaller. Oop. Apparently that's, there we go. The base of the cross section is measured this way, from left to right. The upper function is the curve. The lower function is also the curve, right? Like, so that's the weird part about these things. But we need to get our equation into x equals form because we're perpendicular to the y, so our integral needs a dy. So this is the one thing I kind of wrote myself a note for next year, which hopefully I'll see. Like, if this was kind of missing from any of the examples we did. But what happens is we need to take the y equals x minus 3 but squared minus 5 and solve it for x. So we end up with y plus 5 equals x minus 3 squared. So we end up with, taking the square roots of both sides, x minus 3 equals the square root of y plus 5. But when you're using square roots to solve, you have to drop a plus or minus in the front. You take the square root of both sides, both numbers, the positive and the negative version of that square root will work, should work, could work, and in this case, definitely will work. Last but not least, to get an x equals equation in, I'm just going to add 3 to both sides. So I'm going to write this as 3 plus or minus the square root of y plus 5. All right. So what I really want to do, and the reason I wanted to kind of go over this with everybody too, is to look at these things in Desmos. If we've done this right, we should get the same function. So our original function was y equals x minus 3 squared plus 5. Minus 5, right? I'm going to say that wasn't in the right spot where I drew it. There we go. Okay. Watch what happens when you plug in. Really, we didn't turn y equals x minus 3 squared minus 5 into a function. We actually had to turn it into 2 different functions. Because if we're thinking in terms of flipping the variables around, we're thinking horizontally instead of vertically for line test. This is a function of x, vertical lines, but it is not a function of y because it wouldn't pass the test if we switch roles of our variables. So we actually end up breaking it into 2 separate functions. The first one is x equals 3 plus the square root of y minus 5. Is that what I had written? No. Plus 5, that's where I was wrong at. Yeah. Oop. Ah. And you notice when I type that in, it gives me the right-hand side of the parabola, which, when we're going from left to right, is what we're thinking of as the upper function. And then when I do the 3 minus, hopefully by no surprise, square root y plus 5. That covers up the other side of the parabola. So that's what ends up happening in these problems. There was one I think in the cross sections thing where you had to do the same thing because it was a circle. And this is what happens. Whenever you have to solve something where your x is being squared, and get it in terms of x equals, you didn't have a function of y, you only had a function of x. So you end up with two separate functions, but you kind of needed two separate functions anyway because you had one upper and one lower. All right. So putting this all together, our upper function is the 3 plus, our lower function is the 3 minus. We need to integrate, what do we got? An isosceles right triangle. So when we do an isosceles right triangle, that puts a 1/2 in front of for our coefficient. We're going to integrate. Our upper function is 3 plus square root of y plus 5. Not done yet. And we have to subtract our lower function, which is the quantity 3 minus square root of y plus 5. So that's f of x minus g of x squared. And what are our bounds? I think so. Yep. Because this, we never labeled it, but this is the vertex, which is 3, -5. So we are going from the lowest y value to the highest y value. So -5 to 1. Or sorry, to -1. One of the things that'll happen when you actually go to integrate that is those 3's will cancel. And the y plus 5's will combine. So you actually end up with, you end up with a 1/2 still. And then you just end up with 2 square root of y plus 5, but squared. It actually was one you could probably solve by hand. Be careful, don't cancel those 2's because of the squared. It's 1/2 integral from -5 to -1, 4, y plus 5. And you can cancel that and make that a 2. But yeah. So that's dy on every spot. Yeah. Okay. But again, that one said you could use a calculator if you really wanted to, so you're good there. All right, all I wanted to say for today, you have the rest of the time to work on stuff.